So let's start talking about chapter 14, filters. So this is a very important chapter, and we're going to talk about filters in detail. The first thing that I want to stipulate is that a filter is a system that has a transfer function. It's in the S domain, and I'm going to call that the filter transmission equation. And that is going to be my transfer function, closed loop, and that's going to be the ratio of my output to the input. And I can also express that as a complex quantity in polar coordinates, and also as a function of strictly as a function of frequency, which means j omega. So this transmission looks, so this is the magnitude of my transmission function, and then I have an angle that is also a function of frequency. In general, I'm going to say that the gain, so my filter is going to have gain. These are active filters, by the way, meaning that they have op-amps in them, so I can have gain as part of my filter. So it's going to have a gain that is a function of frequency, defined as 20 log of the magnitude. And the units of that are going to be dB. Okay? Therefore, the magnitude of my output is going to be the magnitude of my transmission expression times the magnitude of my input. So those are important relationships to start with. Now let's talk about filter specifications. If I told you to design a filter, there are some things that I have to tell you in terms of specifications. So let's talk about filters. One, I have to tell you what the edge of the bandpass region is. And that's going to be omega sub p for the passband. I have to tell you what is the maximum allowed variation in the passband. because these are frequency selective circuits, there is going to be a stop band and a pass band, and that's going to be A max. I also need to tell you what is the stop band edge, and that's going to be omega sub s for the stop band. And we want to pass frequencies in the pass band, we want to stop frequencies in the stop band. So stopping something is, another word for it is attenuating it. So I also need to tell you what is the minimum stop band attenuation, denoted by A min. Okay? It's okay to have more attenuation. That's why I say a minimum. So if you are stopping something, it's okay to stop it more to make it smaller, but it's not okay to make it larger. So I need a minimum amount of attenuation, which is the act of making it small or stopping it. And we'll see some pictures, some nice pictures from the book. And again, I'm always trying to balance the, going back and forth in the book. But essentially, these specifications, and again, we'll see a better picture of it. If we just take the case of a low-pass filter, okay, is going, in general, is going to be something like that, and this is going to be the variation in the pass band. So this is A max, and always we have a stop band edge. So this is WP. We can have, this is the pass band edge, this is the stop band edge, and then we want the minimum attenuation in the stop band. So again, it could be more, but there is a minimum. And this is the transition region, pass band, stop band. We'll see a nicer picture, okay? But for now, that puts in context those spec quantities. All right. Now, that transfer function or transmission equation, in general, can be expressed as a rational polynomial in S, where I have a numerator polynomial and the numerator in S as well, with coefficients, appropriate coefficients. So any filter can be expressed as a rational polynomial. Each of these polynomials, the numerator and the denominator, can be factored. into a number of complex factors. So these are the factors of the numerator. Sorry. So we can factor each of the polynomials in S from the numerator and denominator, and you can see clearly the quantity S and these quantities that are complex. The ones that come from the numerator, these are going to be the zeros of the system, and the ones that are related to the denominator are going to be the poles. So these are the poles, and they are complex. Also, by definition, the filter order is defined as the number of poles, so n. Okay? So let's talk about these poles and zeros and what they mean really from a system perspective, then from a circuit perspective, and also from an analytical mathematical perspective. So let's take a closer look at what they do, how they influence the system. So let's talk first about the poles. So as far as the poles are concerned, for the stability, the poles must be in the left hand plane of the S-plane, or the left hand side of the S-plane. Okay? And if we have B coefficients, if you look at the rational polynomial before, the B coefficients are real because I have polynomials in S. But when I factor, the poles and zeros are going to be complex. So don't confuse the coefficients of the polynomials in the rational expression when we had polynomials in the numerator and denominator with the zeros and pole quantities that are complex when we factor those polynomials. The B and A coefficients are real. So these coefficients B, which would be in the denominator polynomial, because we're talking about the poles, they are real. What that implies mathematically is that the P's sub I are either real or they happen in complex conjugate pairs. That's the only way that you can have, when you factor, to have complex poles uh, to get the coefficients to be real, when you multiply those factors, is if the poles happen in complex conjugate pairs or if they are real. If there are only one of them or single ones, that they are real. There are no single complex pole, and there are no single complex pole. Essentially, you can have purely imaginary poles, but since that's an imaginary pole is also a complex pole, they have to happen in pairs. Plus, you don't want them anyway because they would be in the y-axis of the plane, and then technically that is not a pole pair that is in the left-hand side, so that would be unstable. So as we discussed, oscillators will have that that characteristic. Now, one of the things that we want in filters is selectivity, because I want to really pass what I want to pass and really reject what I want to reject in the stop band. That's called selectivity. So for selectivity, the poles must be close to the j omega axis, or the y-axis of the S-plane, which is at odds with stability, because the further the poles are from that axis, the more gain and phase margin we'll see that we will have. But if we really wanted to have selectivity, we want to be close to the axis. So that's a trade-off in design. How much stability margin you have versus how much selectivity you have is a design trade-off. So those are characteristics. Those are characteristics of the poles for the filters in general. Now let's talk about the characteristics of the zeros. The main takeaway from what we discussed before is that the poles define the selectivity. That's a big takeaway from those statements. Let's talk about filter zeros.
Dr. Hernandez, when you say more selectivity, do you mean like a bigger passband, or do you mean like more like accuracy?
No, we would be talking about a sharper or a smaller transition region.
Oh,
so okay. A filter that looks, again, going back to a low pass filter, a filter that looks like that, right, is less selective than a filter that looks like this. Because what am I doing in this part of the spectrum? It's kind of like, you know, I'm rejecting, but I'm also passing, and this is gain, right? So I'm not really, that's less selective than this. Clearly, this one, in this, I have a gain, and here I have a lot of attenuation. And my transition is very narrow. That is selectivity. It's actually quantified by how narrow this is, okay? Versus this. Do you see that?
Yeah, that makes sense. Thank you.
All right, very good. All right, so now let's go back to talk about the filter zeros. Oops. Let's talk about the filter zeros. filter zeros. First characteristic, very important. The zeros determine the type of filter. So that would be low pass, high pass, etc. Because the zeros are located at the what we call stop band frequencies. So think about it. We call them zeros because they made the transmission equation zero. So that's what I want the transmission to be zero, is the stop band. So the zeros are located at the stop band frequencies, including 0, which is DC, and infinity. So these are two cases. So if I have a filter transmission equation that has a 0 at 0, that means that I'm stopping DC, so I have a high pass. If I have a filter that has a 0 at infinity, which mathematically means that I have no real 0, then I have a low pass because I'm stopping everything but the high frequencies. And you'll see that. And then for band pass, there is a mixture or band stop. Another characteristic, that the zeros at a DC, which implies factors of S that look like this, where K is the number of zeros at omega equals 0. That gives you your high pass filter. So you can have that that form. You can also have zeros at infinity. Okay. And then that means that you have a difference in the number of zeros and the number of poles. If you recall, n is the number of zeros, m is the number of poles. Okay. And what you want is that the number of zeros is not greater than the number of poles for stability. In other words, the number of zeros has to be less than the number of poles or equal for stability. So now you start seeing how your poles and your zeros can influence and shape your filter functionality and behavior, and you have a lot of control because you can surgically design these factors mathematically to get the filter that you want, mathematically at least. Then you can map those equations to actual circuit topologies, and then you can map the zeros and the poles to actual components. That's kind of the where we're going with this. But right now, we're just as a purely polynomial level. We don't know what's a resistor, inductor, capacitor yet. These are just polynomials. Another thing to notice is that the transmission is, and this is nice to do because it's convenient as we start getting closer to realizable circuits, is that the transmission can be factored into first order and second order functions. So the first order will give you your real factors, and the second order functions will give you your conjugate pairs. Okay? So we're talking about filters, and we're going to see that we're going to treat them as two-port networks. So we have V in, V out, and the transmission function, which is V out divided by V in, and we're going to be looking at different types of filters, specifically 4 of them. The low pass, we have pass band, and for all of them you have some type of pass band and stop band. High pass, band pass, and band stop. So those are the main 4 that we're going to be looking at. So this figure is very important because this relates to the filter specifications that we discussed. Okay, so here we have, because this is a rational polynomial, you can have variations in the passband. Okay, it doesn't have to be a line. Then we have the transition band that we discussed, and this is the edge of the passband. That's the frequency. And then we have the edge of the stop band. So that would be right here. So here we have the transition. Then we have the Amax spec, which told us how much we can vary in the passband, and then the minimum attenuation, which tells us that in the passband how much it has to be down from the maximum value in the passband. So that's the minimum attenuation. It's okay to be below that, but not okay to be above it. Those are the main specification quantities for filters. So let's see what other. All right, so let's go back. Let's go back to is that we can have this first order and second order functions, and this is convenient because, as you'll see, we're very familiar with first order type of filters, and we are very familiar with second order from prototypes that can be obtained from circuits with capacitors, inductors, and resistors. Okay? So when we have a first order filter, we call that a bilinear transfer function. And it has this form. Where we have a zero, we have a single zero at A0 over A1 in this equation here. And we have a single pole at minus omega naught. So that's the general expression for a first order filter that we call a bilinear transfer function. So for example, a Miller integrator fits that general formulation. And then we have the second order functions as well. And again, any type of rational polynomial of any order or any type of filter of any order can be factored into these first and second order systems that we can basically concatenate and obtain the higher order one. And that's why we're talking about factoring into first and second orders, is because a lot of the times when we're going to do or realize high order filters, what we do is we concatenate combinations of second and first order filters that we can make easily with circuits. So the second order which we call biquadratic transfer function looks like this in general. Like that. That is the preferred model for a biquadratic transfer function. The most notable thing in the biquadratic transfer function is you have a complex conjugate pairs of poles. So you have two poles, and we said that the poles, if they are in pairs, or if they are complex, they must be in conjugate pairs. So we have two poles which are at this complex conjugate S value. If you solve, just applying the quadratic equation to the denominator, okay? And that is the general case. So now we can look at some interesting cases and specific cases of this quadratic transfer function. The low-pass filter. So low-pass filter, we said that it has the zeros at infinity, meaning that there are no zeros that are real. So for a biquadratic low-pass filter, the transfer function would look like just a constant. So there are no zeros, and there's just a DC gain, or part of it. And then the denominator and towards the end I'm going to show a figure versus frequency of this equation, and what you see is that it changes according to these parameters. Most notably, the shape changes because of Q, and Q is called the selectivity of the filter. We'll see that we have some type of sort of overshoot or peak at the beginning of the transition if Q is higher than 1 over the square root of 2. If Q is equal to 1 over the square root of 2, we'll see that the shape of that frequency response is maximally flat. Now you can see that if you want a filter to extract DC, you want flatness in the passband, which is where you want the DC to be extracted from. So you will want a filter like this to extract DC component of any type of signal. And then if Q is less than 1 over the square root of 2, that's the third possibility, then that implies that you have you don't have maximum flatness, but you have a nice roll-off in the frequency response. Other things that are interesting about this formulation of filters with these equations is that you can get the high-pass transfer function by just subtracting the low-pass from 1. So the mathematics works really nice. Okay? So that's what I'm going to stop today. I want to show you another figure, but I'm going to stop today here, and then on Tuesday we'll keep talking at this level about the bandpass and notch and other types of realization and other types of filters, specific types of polynomials that people have studied that give us certain characteristics. So let me exit this. These are the cases for different values of Q. So depending on the value of Q, you have a peak if Q is greater than 1 over the square root of 2. If it's equal to this 1 over the square root of 2, you get this maximum flatness here. I mean, this is supposed to be flat, and you got an. And if it's less, then you get sort of a nice roll off. So that's essentially how your frequency. This is the magnitude of the transmission function or the transfer function over frequency. So that's how the Q impacts the shape of the frequency response of the filter.